All right, this is going to be an introduction to Chapter 12, which is kinetics. Chapter 12 sometimes confuses people. The whole topic of kinetics can be a little bit daunting, but hopefully I'll be able to break it down for you into nice, manageable, bite-sized pieces. One reason kinetics is confusing, any kinetics chapter they're going to talk about a rate of a reaction. They're going to talk about a rate law. They're going to talk about a rate constant, which is this lowercase letter k. Whatever you do, don't mistake this lowercase letter k with the big letter K. Big letter K is the equilibrium constant. We've already covered equilibrium. And big K is an equilibrium constant. A little k is a rate constant. Just to make matters more confusing, there's a rate law. And then there's this other beast called an integrated rate law. So you have rate. It can be a little daunting. Don't let that freak you out. Right now, I want to get into what is a reaction rate and what is a rate law, and more importantly, how do you determine a rate law for a reaction? Okay, rate of a reaction. The rate of anything, what a rate is a change in something over a change in time. I mean, if you bicycle from here to Santa Fe, and that's 50 miles, so your change in distance is 50 miles. Let's say that bike trip takes you 5 hours. 50 miles, 5 hours. What's your rate of travel? Well, you're cycling along at a rate of 10 miles per 1 hour. So a change in distance over change in time gives you your rate of travel. For a reaction in chemistry, we're not worried about change in distance. In chemistry, we're worried about the change in concentration of something divided by the change in time. So let's find a rate. Let's look at this reaction here. Two of these things, that's ICl, iodo-chloride. 2 molecules of iodo-chloride react with hydrogen to form 2 molecules of hydrochloric acid and 1 molecule of iodine, I2. So let's say you're looking at a reaction. You've got a reaction mixture, and you find that the concentration of HCl at some point in time happens to be 3.2 molar. So you got your reaction mixture, you got your flask here with the reaction going on. The HCl has this concentration. 60 seconds later, same flask. The HCl has this higher concentration. What is the rate at which hydrochloric acid is being formed? Well, what is the rate? Change in concentration over change in time. So change in the molarity of the HCl divided by the change in time is the rate. Well, in this particular case, how did the concentration change? Oh, it ended up at 3.56. So it's 3.56 molar minus 3.2 molar. And to effect that change, it took 60 seconds. And if you do the math there, you come out with, the hydrochloric acid is being formed at a rate of 0.006 moles of HCl per liter per second. So that's your rate at which you're forming hydrochloric acid. So for every 1 liter of the reaction, you're going to make that many moles of the HCl per second. Okay, now one skill that you have to get good at here is changing the rate in terms of one chemical into the rate in terms of a different chemical. It's pretty easy. This is simple stoichiometry. But anyway, here's that reaction all over again. So two of these react with one of these, and it forms two HCl's and one iodine, I2. Hey, if the HCl is being formed this fast, is that how fast the I2 is being? No, of course not. One quick look at this, and you can tell that you're making this chemical twice as fast as you're making this one, right? You're making two of these for every one of these. So you have to be able to interconvert between chemicals. And that is simply stoichiometry. Nothing fancy here that you haven't seen before. So again, here's your reaction all over again. Two of these react with that to get two of these and one of these. We found the rate at which you're forming HCl. The previous example, it says that HCl is being formed that fast. What is the rate of formation of I2? Well, real simple thing. Let's start with what we know, 0.006 moles of HCl per liter per second. I'll just use S for seconds. That's how fast you're making hydrochloric acid. That's how fast you're making this. How fast are you making this stuff? Oh, use a mole-to-mole ratio. Simple stoichiometry. Turns out you get 1 I2 for every 2 HCl. So one of these for every 2 of these. Notice how the HCl cancels out. And it's going to give you 0.003 moles of I2 per liter per second. So that's how fast you're producing this chemical. That's the rate at which you're producing iodine. Now, one thing I don't want you to get too hung up about, but the books cover it, so I better cover it. The rate of the reaction. So far, all we've really talked about is the rate at which we're making this chemical, which is different than the rate at which we're making this chemical. The rate of the reaction, how do you get that? Oh, it turns out if you get a rate in terms of a particular chemical and you divide it by the coefficient from the reaction, that gives you the rate of the reaction. So the rate of the reaction is going to come out the same no matter which chemical is being measured. For instance, we just found in that above example, hydrochloric acid is being formed this fast. Iodine is being formed this fast. What's the rate of the reaction? Oh, well, the rate of the reaction here, the rate of your reaction is going to be 0.006 all over, what's that coefficient? Oh, 2, which is going to give us 0.003 moles per liter per second. Hey, rate of the I2 is being formed. I2 was being formed this fast, so the rate of the reaction is going to be 0.003 divided by, what's our coefficient? Oh, 1. So you get the same rate of reaction no matter what if you simply normalize it by dividing by the coefficient. Now, when you're working a problem, guys, I almost never will ask you for the rate of the reaction. I'll ask, what's the rate at which you're making this stuff? What is the rate at which you're making this particular chemical? What's the rate at which this chemical is disappearing? So, you know, if you absolutely have to find rate of reaction, oh yeah, divide by the coefficient and you're there. Anyway, let's see. The general equation for what I just showed you, the rate of a reaction, the book makes it look so confusing. if here's your reaction, these are your chemicals, A, B. These are the coefficients. That little a is the coefficient to balance the reaction. What's the rate? The change in the concentration of A all over the change in time. Change in A, that little delta means change. Change in the concentration of A all over the change in time. And you also have to throw in a number for the coefficient. That'll give you the reaction rate. But again, I'm not going to be asking about reaction rates. I'm going to be asking, hey, what's the rate at which you're making this stuff? Or the rate at which you're making this stuff. Real quick, let's take a look at when you measure a reaction rate. Can you measure a reaction rate at any point in time? Well, yeah, you sure can. But for most reactions, for the vast majority of reactions, the rate of the reaction changes over time. Most reactions start out real fast, and then they start to slow down. What we really want, typically, we want to find the initial rate of a reaction. So you measure that rate of reaction right at the very beginning. That gives you your initial rate of reaction. And if you look at the next page here, this is giving you a graph, concentration of C, so one of the products here. This would be looking at the rate at which you're forming C. So you got the concentration of C here, you got time here, and if you make a graph of the concentration versus time, for most systems it starts off as kind of a straight line. It looks like a straight line, but over time you start to realize it's not a straight line, it's a curve. The rate of the reaction is the slope of this line. So initially it's a nice straight line. Yeah, you can find a slope. You can measure the concentration of C here, concentration of C here, time here, time, slope. Remember from algebra, slope of the line is the change in y all over the change in x, which in this case would be the change in the concentration of C all over the change in time. So the slope is really your rate. But again, initially your slope is kind of steep. Over here your slope is less steep. Over here you have no slope. Over here it kind of flatlined, right? There's no slope at all. What's going on here? Oh, you've hit equilibrium. When the concentration isn't changing anymore, then you're at equilibrium. So what we're interested in is the initial rate, typically. For what it's worth, your book will occasionally talk about an instantaneous rate. Like I mentioned to you here, the rate initially is different than the rate later in time. If you had to find what's the rate of the reaction at this point in time, right here, that point in time, what's the rate of the reaction? Oh, it's the slope of the curve taken at a single point, which might seem odd to you if you haven't taken calculus, but it's essentially the tangent there. Don't worry, this isn't going to be on a test, but hey, if you drew a tangent line here at that point, the slope of this line is the rate at this point in time. If you've had a little calculus, you realize, hey, if you know a function that describes this curve, you can take the derivative, and that gives you, the slope of the curve at a point. Anyway, don't lose sleep over that. No, you don't have to know any calculus for this stuff. But if you've had calculus, that's one of the applications of it. Okay, let's take a look at the rate law. That's really the crux of this set of notes, is you being able to determine a rate law. For any particular reaction, you can write a rate law. The rate law is always written in terms of the reactants, not the products. We don't really have these in the rate law. We only have the reactants in a rate law. How fast is that reaction going? Oh, the rate of the reaction equals this lowercase k, which is the rate constant. So your lowercase k is your rate constant. So it's that rate constant times the concentration of your reactants, each raised to some power. Don't make the mistake of thinking that this power here is related to that coefficient. It is not. All through equilibrium, we kept raising things to the power that matched the coefficient in the equation. We don't do that in kinetics. In kinetics, these numbers here have to be empirically determined. Empirically determined means you got to do some experiments and measurements. And from those measurements, you can determine these powers. They are not necessarily related to the coefficients. No way, no how. Now, these powers are called the orders. So M here would be the order in A. Sometimes you'll hear it called the order with respect to A. N would be the order with respect to B, or simply the order in B. What in the heck are reaction orders? Well, the best way to think of them is they're sensitivity factors. The bigger this number is, the more sensitive the rate of the reaction is to this concentration. For some reactions, this number might be a 0. You would say it's 0 order in B. What's that mean? Oh, well, anything raised to the 0 power is 1. You know, if you had 25 and you raise it to the 0 order, it's 1. What's that mean? Oh, it means that concentration doesn't matter. So 0, if that number is a 0, that means the concentration of that stuff has no effect on how fast the reaction goes. So think of them as sensitivity factors. And the crux of this set of notes is teaching you how to find a rate law. If there's some problem you see that says determine the rate law or find the rate law, what it really means is find those numbers. That's what finding a rate law means. So let's show you how that works here. And this kind of repeats what I just told you. These powers are not related to the coefficients in the equation. They're called the reaction orders, or the order in each thing. It's a sensitivity factor. Tells you how sensitive the rate is to that particular substance. If we take a look at this thing, you'd say that this reaction is first order in A. It is first order in B. And you'd say it's second order overall. How do you get that overall order? Oh, you just add up the two numbers. That's the overall order. So first order in A, first order in B, second order overall. What does it mean that it's first order in A? It means that if you take this number, the concentration of A, and you make it twice as big, the reaction is going to go twice as fast. The rate goes twice as fast because you made this twice as big. That's all that really means. Now, let's take a look at this rate law. Got first order in A, second order in B. It's third order overall. What does being second order in B means? Hey, it means that the rate of the reaction is much more sensitive to this particular reactant than to this one. Being second order means if I make the concentration of B twice as high, the reaction is going to go 4 times as fast. So if I make this number twice as high, well, what's 2 squared? 4. So double the concentration of B, and you will quadruple the rate of the reaction. So it's more sensitive to the concentration of B. So again, these orders are sensitivity factors. Now, to find a rate law, let's walk you through an example where you have to determine a rate law here. Find a rate law. You look at tables of data. This is experimental data that somebody has to collect. Somebody has to go into a lab. They got to run the reaction at under different conditions, different concentrations of each thing. They collect rate data. It's not easy, guys. The people that do this kind of work, I admire them. This is tough work finding this type of data. But anyway, let's say you're given a table of data like this for this reaction. A plus 2B turns into a C. And you're asked to determine the rate law. When it says determine the rate law, oh, I could write the rate law without even looking at that table. The rate law is the rate equals K times the concentration of A to some power, let's call it X, and the concentration of B to some power, let's call it Y. Hey, when they say determine the rate law, they're saying, what is that number? What's the order in A? What is that number? What's the order in B? Okay, to do that, you got to look at the tables. Now, if we go for the order in A, so I want to find out how sensitive the rate is to this concentration of A. Well, I got all kinds of, if they ran it at this concentration, then they doubled the concentration, then they quadrupled it, etc., etc. What you want to do is find 2 trials where the concentration of A changes, but the concentration of B stays the same. By keeping the concentration of B the same, you're kind of taking this guy out of the picture. The concentration of B has not changed. You're only changing one variable at a time. If you look at this, going from here to here, you doubled the concentration of A. What happened to the reaction rate? Oh, it changed by quite a bit. Initially, you might go, God, well, I doubled this. I can see that that went up by a factor of 2. How much did this go? If you have to, just rip out a calculator. Divide the bigger number by the smaller one. So for this one, I got, what do I have here? This rate, 2.2 times 10 to the 5th. 2.2 times 10 to the 5th. Divided by 5.5. 5.5 times 10 to the 6th. Yeah. 2.2 times 10 to the 5th. Divided by 5.5, 10 to the 6th. Oh, no, I did something wrong there. 2.2, 10 to the negative 5th power, divided by 5.5, 10 to the negative 6th power, 4. Oh, hey, so this went up by a factor of 2. This increased by a factor of 4. So I doubled the concentration of A, and the reaction is going 4 times faster. That tells me that this number is a 2. So my rate law has now boiled down to the rate equals K times A squared B to some power Y. So again, the way I got this, I picked 2 trials where B is not changing. I want to see what's the effect on the rate of the concentration of A. I doubled the concentration of A. I quadrupled the rate. He's second order in A. Okay, let's tackle B. To find the order in B, I want to find two trials. I'd want to find two trials where the concentration of A stays the same. If we were to look at trials 4 and 5, A is not changing, but the concentration of B was doubled. So I'm doubling the concentration of A. Doubling the concentration of B. How did the rate change going from here to here? Well, 3.3, 10 to the negative fifth. We'll do our, not too much glare there. 3.3 times 10 to the negative fifth divided by the other rate, 1.65, 2. So, I doubled the concentration and the whole thing started to go twice as fast. That's telling me that this number is a 1. So you double your concentration, you double your rate, that's a 1. So you'd say the overall rate law is your rate constant K times the concentration of A squared times the concentration of B raised to the first power. That's how you find a rate law. You look at tables of data like this, and you see how changing the concentration affects the rate. This particular reaction, the rate is more sensitive to the concentration of A than it is to the concentration of B. Hey, the second part of this example says, find the value of the rate constant K. So you want a number here. Right now, we don't have a number, do we? How do you find that? Pick any trial. Any of these trials will give you the same answer. Let's pick on trial 5. You'd say the rate in trial 5, the rate is 3.3, 10 to the negative fifth. So you'd say 3.3 times 10 to the negative fifth. That's your rate. That's equal to the rate constant, K, times the concentration of A, which is 0.100 squared. A in trial 5, the concentration of B is 0.600 to the first power. If you take this thing and solve it for K, you'll end up with your rate constant. Without doing all the algebra, I'm sure you could do this on your own. K should end up being 5.5 times 10 to the negative third. So to find the rate constant, once you know the rate law, once you know these orders, pick any trial, plug in the rate, plug in the concentrations, solve for the missing piece. There's two more examples here. I don't think I'm going to have enough video time to go through them both, but the notes I gave you has the solutions on them. So you might want to tackle these on your own. See if you can find the rate law for this one. See if you can find the rate law for this one. And again, the answers are on the back of the note packet that I gave you. So hope that gets us off to a decent start on kinetics. And we'll continue with kinetics when I get back.